Today, the observable universe is a sprawling, structured expanse, stretching roughly 93 billion light-years in diameter. It is packed with billions of galaxies, glowing with the light of countless stars. But to understand what occupies that immense space, we must look at the exact mass-energy inventory gathered by the European Space Agency's Planck satellite mission. This pie chart breaks down the cosmic inventory, and the data reveals a massive imbalance. Every single star, planet, dust cloud, and living thing, everything that makes up ordinary baryonic matter, accounts for roughly 4.9% of the universe. The overwhelming majority of the cosmos is entirely invisible to us. About 26.8% is dark matter, an unseen mass holding our galaxies together. The remaining 68.3% is dark energy, a mysterious force actively driving the universe apart. To figure out how we ended up with such a highly specific, lopsided inventory, we have to treat the universe like a giant thermodynamic engine. We need to rewind the clock 13.8 billion years to a time when all of this space was infinitely hot. At the very beginning, during the Planck epoch, the universe was an initial singularity. At an incomprehensible 10 to the 32nd power Kelvin, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were entirely crushed together into a single superforce. A fraction of a microsecond later, the universe entered the inflationary epoch. Space itself expanded faster than the speed of light. It ballooned from the size of a subatomic particle to the size of a grapefruit in an instant. This violent stretching forced the first critical drop in temperature. As the universe cooled, gravity, followed closely by the strong nuclear force, finally broke away from the initial superforce. By the end of its frantic first second, the fabric of the cosmos had permanently smoothed out. It was left as a chaotic, seething soup of colliding matter and antimatter, waiting for the next deep freeze. Within the first few minutes, the universe crossed its next major thermodynamic threshold, rapidly cooling down below 1 trillion Kelvin. Below this temperature, subatomic particles called quarks could no longer survive on their own. The strong nuclear force bound them together, forcing them to create the universe's first stable protons and neutrons. For the next 17 minutes, the entire universe operated like a giant stellar core. During this period, known as Big Bang nucleosynthesis, those newly minted protons and neutrons fused together to forge the very first hydrogen and helium nuclei. The physical nuclei for all the ordinary matter we see today were successfully forged right here. However, the ambient heat of the universe was still far too intense for electrons to attach to them. The universe remained structurally incomplete, and as a result, utterly opaque. For the next few 100,000 years, the cosmos existed as a glowing, blinding fog of plasma. Photons, the basic particles of light, were completely trapped, constantly bouncing off a chaotic swarm of free-roaming electrons. The turning point finally arrived 380,000 years later. Space cooled down to roughly 3,000 Kelvin. This allowed the hydrogen and helium nuclei to finally capture those slowed-down electrons, forming the first true neutral atoms in a milestone known as recombination. The physical consequence was immediate. With the free electrons suddenly swept up into atoms, the trapped photons were able to travel straight across space, entirely unimpeded. This image maps out the cosmic microwave background. It shows the exact initial flash of freed light from recombination, which has been stretched by expanding space into microwave frequencies that we can still detect in every direction today. As space continued to expand, that incredible afterglow stretched out of the visible spectrum and faded into the infrared. The newly transparent universe went pitch black, entering a period known as the Dark Ages, as a massive, expanding cloud of neutral hydrogen. Deep within that freezing darkness, gravity went to work. Over millions of years, it gathered denser pockets of hydrogen gas together, crushing them until the localized pressure ignited the very first massive, luminous stars. These giant population 3 stars burned fiercely, reionizing the surrounding space before dying in massive supernovas. Their explosive deaths seeded the universe with the first heavy elements, like carbon, oxygen, and iron. Over the next several billion years, gravity pulled these new elements, along with vast amounts of dark matter, into the first galaxies. About 4.6 billion years ago, a specific localized cloud of gas and dust collapsed to form our own sun and solar system. Gravity served as the master architect of this era. It successfully took that 4.9% of ordinary matter and assembled it into the complex planetary systems and stellar structures necessary for life to exist. This graph charts the universe's expansion speed. For its first half, the gravitational pull of newly formed matter applied the brakes, slowing expansion. But 4 billion years ago, as matter spread apart, the universe hit an inflection point. Dark energy overpowered gravity. Dark energy took over as the dominant force in the cosmos. Instead of slowing down, the expansion of the universe began to accelerate, stretching space apart faster and faster every day. We often treat the 13.8 billion-year story of cooling and complex assembly as a finished chapter of history, but it is an actively ongoing thermodynamic process. Today, that process is driven entirely by dark energy, pushing that tiny 4.9% of ordinary matter outward toward a vast, unknown future.